The Sunday just did something terrifying, and it's not over yet. A massive hole tore across its surface, unleashing a river of plasma straight toward Earth. And at that exact moment, the interstellar visitor, Comet 3IATLAS, vanished from every telescope on Earth. Poof, just gone. Then Mother Earth shook with an earthquake. Now, one question is on everyone's mind: what happened? Was the comet destroyed, transformed? And if it ever re-emerges, what will it look like then? If it re-emerges at all? As one comet slips into hiding, another bursts into the spotlight. Comet Lemmon, an icy relic that's older than human civilization itself, is racing across our skies. We're breaking down why the next 2 weeks are going to be make or break. Meanwhile, in China, physicists have pulled off something that sounds like pure science fiction: an unhackable quantum communication network. Oh nay, that's basically a total snitch. Any interference gets caught red-handed. And don't blink, before we wrap up, we'll reveal the cosmic dates you cannot miss, including one everyone's ignoring right now, but shouldn't, if these mysteries have you on edge the way they have me. Don't just watch, take action. Hit like, smash subscribe, and stay locked in as these stories unfold in real time. Drop a comment with where you're watching from, what time it is there, and tell me straight, do you believe we're being told the whole truth about these world-shifting discoveries? And if you want to help this community grow, share this video on X, Facebook, Reddit, or even your group chats. Every share, every comment, every click is fuel for the hunt. You're the reason we can keep chasing these stories. So thank you for standing with us in the search. Part 1. The Disappearance. The Sunday just did something terrifying. October 2025 arrived with a cosmic alarm bell that most people never heard. Scientists monitoring our star watched in growing unease as a massive trans-equatorial coronal hole ripped open across the solar surface, a gash in the Sunday's magnetic field that looked like a wound bleeding invisible energy into space. This wasn't your typical solar activity, the kind that produces pretty auroras and maybe disrupts a few satellite signals. The hole was enormous, spanning regions of both the northern and southern solar hemispheres simultaneously, a configuration that happens rarely, with consequences we're only beginning to understand. The solar wind that poured through this tear in the Sunday's magnetic armor reached speeds of 700 kilometers per second. To put that in perspective, imagine a hurricane where every particle of air is moving at nearly 1.5 million miles per h-hour. The stream of charged particles, protons and electrons stripped from their atoms, came screaming toward Earth like a cosmic fire hose aimed directly at our planet's magnetic field. The alignment was perfect, almost suspiciously so. The magnetic polarity of the solar wind matched Earth's field orientation, in precisely the configuration needed for maximum coupling, the strongest possible transfer of energy from the Sunday's breath into our planetary magnetosphere. Geophysicists scrambled to predict the impacts. Power grid operators received warnings. Satellite controllers prepared for possible malfunctions. Aurora chasers packed their cameras and headed north, knowing this kind of solar assault would paint the sky in colors that defy description. But something else happened at that exact moment. Something that turned this solar event from a routine space weather episode into a genuine cosmic mystery. Comet 3IATLAS, the second confirmed interstellar visitor ever detected in our solar system, disappeared behind the Sunday. One moment, it was there. A faint smudge of light moving on an orbit that originated in another star system, carrying ice and rock that formed in alien clouds around a sun we'll never see. The next moment, it vanished into the solar glare swallowed by the overwhelming brightness of our star, rendered invisible to every telescope on Earth and in space. The timing was impossible to ignore, Earth's magnetic field getting hammered by the fastest solar wind in months, and simultaneously, our only accessible interstellar messenger going dark behind the very source of that assault. Scientists are careful people, trained to avoid jumping to conclusions. Conditioned to repeat the mantra that correlation does not equal causation, they measured their words carefully when reporters asked if these events could be connected. Then the earthquake started. Multiple magnitude 7 earthquakes struck different regions of Earth within hours of the solar wind's arrival. Seismometers recorded the violent shaking, the sudden release of tectonic energy that had been building for years, perhaps decades, in the stressed rock beneath our feet. The tremors were not unexpected in a statistical sense. Earth experiences roughly 15 magnitude 7 earthquakes every year, on average. But having several occur in close temporal proximity to a major solar event, and the disappearance of an interstellar comet triggered something in the human pattern recognition system, that ancient part of our brains that searches for connections, that demands meaning from coincidence. Could the Sunday's magnetic assault on Earth have somehow triggered seismic activity? The mainstream scientific consensus says no, that's not how earthquake physics works. Tectonic plates don't care about magnetic fields or solar wind. They grind and slip according to the laws of rock mechanics and accumulated strain energy. But there are other voices, researchers working at the fringes of geophysics, who point to statistical anomalies in earthquake timing during solar maxima, who suggest mechanisms involving ionospheric coupling or subtle changes in Earth's rotation rate. These ideas haven't gained traction in peer-reviewed literature, but they circulate in conference hallways and online forums, whispered possibilities that the mainstream hasn't yet disproven to everyone's satisfaction. The comet, though, that's where the real mystery lives. 3IATLAS earned its designation as the third confirmed interstellar object detected passing through our solar system. The first was 1I Oumuamua in 2017, that bizarre elongated thing that tumbled through the inner solar system and exhibited acceleration that couldn't be fully explained by normal comet outgassing. The second was 2I Borisov in 2019, which looked and behaved more like the comets we're familiar with, a reassuring ball of ice and dust that followed predictable physics. 3IATLAS was discovered in 2025, tracked as it fell toward the Sunday on a hyperbolic orbit, moving too fast to be bound by our star's gravity. Clearly a visitor, just passing through on its way back to interstellar space. These objects are incredibly precious to science. They're the only samples we have of material from other stellar systems, at least until we develop the technology to send probes to nearby stars and return with physical specimens, something that won't happen in any of our lifetimes. Every photon of light we collect from an interstellar comet carries information about chemistry, about the composition of protoplanetary disks around other suns, about whether the processes that formed our solar system are universal or unique. When 3IATLAS disappeared behind the Sunday, we lost our ability to gather that data, at least temporarily. The question that haunts astronomers now is simpler and more disturbing than any of the speculation about solar wind or earthquakes. When 3IATLAS emerges from behind the Sunday, if it emerges at all, will we recognize what comes out? Did the Sunday just eat our interstellar visitor? Could the intense heat, radiation, and magnetic turbulence near our star have reshaped it, broken it apart, vaporized it entirely? We're about to find out, and the answer might upend everything we think we know about these alien wanderers. Part 2. The Traveler We Lost. The story of 3IATLAS begins like most comet discoveries do, with patience, with automated telescopes scanning the sky night after night, looking for anything that moves against the background stars. The ATLAS survey, short for Asteroid Terrestrial Impact Last Alert System, consists of 4 robotic telescopes distributed around the globe, designed primarily to spot asteroids that might pose a collision threat to Earth. The telescopes don't discriminate. They capture anything that moves, including comets. And in the early months of 2025, they captured something extraordinary. The object appeared first as a faint streak in images from the Hawaiian stations. Follow-up observations from other facilities confirmed it was moving, and moving fast. Trajectory calculations revealed the telltale signature of a hyperbolic orbit. An eccentricity greater than 1, meaning this thing wasn't bound to the Sunday, it came from somewhere else, and after its close approach to our star, it would leave, headed back into the cosmic ocean between stars. Its orbital energy was wrong for a solar system native. This was interstellar. The astronomy community mobilized quickly. Telescope time, always scarce and competed for months in advance, was suddenly made available. Spectroscopy, the analysis of the light reflected or emitted by the comet, became the priority. What was this thing made of? Did it contain the same mix of water ice, carbon dioxide ice, and organic molecules that characterize comets born in our solar system? Or would its composition reveal alien chemistry, ratios of elements that pointed to formation conditions around a different type of star? Early data suggested something puzzling. The brightness of 3IATLAS didn't behave quite like astronomers expected. Comets typically brighten as they approach the Sunday, following a predictable curve related to the increasing sublimation of ice. As solar heating intensifies, water ice starts subliming, turning directly from solid to gas when sunlight warms the surface to around 200 Kelvin. Other volatiles like carbon monoxide and carbon dioxide sublime at even lower temperatures, creating activity at much greater distances from the Sunday. 3IATLAS's brightness curve showed flattening periods, where the comet didn't brighten as much as models predicted, followed by sudden jumps in luminosity that suggested discrete outbursts of dust or gas. The coma, the fuzzy cloud of gas and dust surrounding the nucleus, appeared unusually faint in some observations. Dust production seemed lower than expected for a comet of its size. Some researchers speculated the nucleus might have an unusually high density, more rock than ice, which would explain the weak activity. Others suggested the opposite, that the nucleus was extremely porous, almost like a rubble pile held together by weak gravity, and that this structure was causing the ice to sublimate in unpredictable bursts rather than steadily. Then there were the non-gravitational forces. Comets don't follow pure Keplerian orbits, paths determined solely by the Sunday's gravity. When ice sublimates from the nucleus, it creates jets of gas that act like tiny rocket engines, pushing the comet slightly off its predicted path. These non-gravitational accelerations are small but measurable, and they introduce uncertainty into predictions of exactly where a comet will be at any given time. For 3IATLAS, these perturbations were particularly difficult to model. The orbit calculations kept getting refined, the error bars kept shifting, and astronomers grew increasingly uncertain about precisely when and where the comet would reappear from behind the Sunday. Some observations hinted at possible fragmentation before the disappearance. Comet nuclei are fragile things, weakly bound collections of ice and rock that can split apart under thermal stress or tidal forces. When a comet fragments, it often creates a train of smaller pieces following similar orbits, sometimes visible as multiple condensations in the coma. Imaging of 3IATLAS showed possible asymmetries, elongations that might indicate the nucleus was beginning to come apart. If the comet was already fragmenting before it disappeared, the question becomes even more pressing. What will emerge from the solar glare might not be a single object, but a stream of debris, or perhaps nothing at all if the fragments became too small to detect. The comparison to previous interstellar visitors was inevitable. 1I Oumuamua, the first detected interstellar object, was never confirmed to be a comet. It showed no visible coma, no dust tail, nothing that would definitively identify it as an icy body. Yet it accelerated away from the Sunday in a manner that couldn't be explained by gravitational forces alone. The most likely explanation remained comet outgassing, but of a volatile more exotic than water, possibly carbon monoxide or molecular nitrogen, substances that would sublime without producing visible dust. The alternative explanations, from light sails to alien probes, captured public imagination, but found little support among scientists who deal in evidence rather than speculation. 2I Borisov behaved more like a familiar comet with a proper coma and tail, and brightness variations that matched standard comet models reasonably well. Its spectrum revealed water vapor and carbon monoxide chemistry, similar to what we see in solar system comets. This was reassuring in a way. It suggested that planetary formation around other stars follows similar rules, produces similar objects. But Borisov also showed signs of fragmentation near perihelion, its closest approach to the Sunday. Images captured what appeared to be a small chunk breaking away from the main nucleus. A reminder that these interstellar travelers don't always survive their passage through the inner solar system intact. Now 3IATLAS was following a similar path, diving toward the Sunday, and we'd lost sight of it at the worst possible moment. The geometry of solar conjunction when an object passes behind the Sunday, as seen from Earth, creates an observation gap that can last days or weeks depending on the object's trajectory and brightness. For a faint comet already showing signs of unusual behavior, this gap becomes a black box, a period where anything could happen, and we'd have no way to know. The comet could be disintegrating. It could be brightening dramatically. It could be intact and simply too close to the Sunday's glare to see. We wouldn't know until it emerged. If it emerged, models attempted to predict what would happen based on assumed nuclear sizes and compositions. If the nucleus was large and mostly rocky, thermal models suggested it would survive with minimal mass loss. If it was small and icy, the heat near perihelion could vaporize it completely, leaving nothing but a dispersing cloud of gas and dust. The uncertainty in nucleus size was enormous, ranging from a few hundred meters to several kilometers. A factor of 10 or more, and that uncertainty propagated through every prediction model, turning forecasts into guesswork. The phrase astronomers kept using was invisible interstellar traveler, somewhere behind the Sunday's glare, hidden from every telescope humanity has built. An object from another star system was either surviving or dying, and we could do nothing but wait and wonder what would emerge when the geometry finally allowed observation again. The wait felt like an eternity compressed into days. Part 3. When solar wind meets alien ice. The Sunday isn't a gentle thing. We think of it as our benign, life-giving star, the warm light that makes Earth habitable. But up close, the Sunday is violent, chaotic, a roiling ball of plasma where temperatures reach millions of degrees and magnetic fields twist into configurations that store energy like loaded springs. When those springs snap, the results can be catastrophic for anything nearby. The coronal hole that opened in October 2025 was one of those events that makes solar physicists nervous. Coronal holes are regions where the Sunday's magnetic field opens up into space rather than looping back to the surface. These open field lines act like highways for solar wind, allowing plasma to escape into the solar system at high speed. A typical solar wind speed is around 400 kilometers per second. The wind pouring from this particular coronal hole was moving at 700 kilometers per second, nearly twice as fast, carrying more momentum, more energy, more potential for disruption. When solar wind at those speeds encounters a comet, the interaction becomes complex and violent. Comets are not magnetically shielded like Earth. They don't have a magnetosphere to deflect the charged particles. Instead, the solar wind slams directly into the coma, the cloud of gas and dust surrounding the nucleus, and strange physics takes over. The gas in the coma becomes ionized by solar ultraviolet radiation, creating a population of electrically charged molecules. These ions respond to magnetic fields, and the solar wind carries frozen in magnetic field lines that drape around the comet like a cape. The result is a magnetotail, a structure formed by the interaction between the solar wind's magnetic field and the ionized gas from the comet. This tail can extend millions of kilometers downstream, away from the Sunday, glowing faintly in the light of ionized carbon monoxide and other molecules. The tail is not a passive structure. Turbulence in the solar wind causes it to wave and flutter. Disconnection events can occur where the tail breaks off entirely and a new one begins to form. These interactions are visible from Earth with the right instruments, and they provide clues about both the solar wind conditions and the comet's gas production rate. But what happens when a comet encounters an exceptionally fast solar wind while already stressed by intense solar heating near perihelion? History provides some terrifying examples. Comet Ison, discovered in 2012 and predicted to become spectacularly bright, disintegrated during its close pass by the Sunday in 2013. Images from solar observing spacecraft showed the comet entering the perihelion region as a bright object and emerging as nothing but a dispersing cloud of dust. The nucleus apparently broke apart completely, unable to withstand the thermal and tidal stresses. Comet Lovejoy, a sungrazer that passed within 140,000 kilometers of the solar surface in 2011, somehow survived, despite predictions it would be destroyed. Images captured the comet's tail extending millions of kilometers after perihelion, fed by massive gas production from the superheated nucleus. The survival of Lovejoy was unexpected and still not fully explained. Some combination of nuclear size, composition, and structural strength allowed it to endure heating that should have vaporized it entirely. 3IATLAS was not passing as close to the Sunday as those extreme sungrazers, but it was entering the region where solar influence becomes dominant, and it was doing so during a period of unusually intense solar wind. The question became whether the combination of factors, thermal stress, plus radiative heating, plus solar wind pressure, plus possible prior fragmentation, would be enough to destroy it. Some researchers proposed more exotic interactions. The electric comet model, promoted by a small group of plasma physicists, suggests that comets develop electrical charges as they interact with the solar wind, and that electrical forces, not just thermal sublimation, drive comet activity. Mainstream astronomy has not embraced this model, finding that conventional physics explains observations adequately without invoking electrical effects. But proponents point to phenomena like disconnection events in comet tails and rapid brightness changes as evidence that electrical processes play a role. The hypothesis extends further into fringe territory with suggestions that strong solar wind events could induce charge separations in a comet's coma, separations that might, under certain circumstances, cause explosive disruptions or trajectory changes beyond what's expected from simple outgassing. The evidence for these claims is contested, the theoretical framework incomplete, but the ideas circulate because they attempt to explain observations that don't quite fit standard models. When 3IATLAS disappeared during a major solar wind event, those promoting electric comet models saw potential confirmation of their ideas. Mainstream astronomers saw an unfortunate but ultimately coincidental overlap of events. What makes the situation more uncertain is that we don't actually know what 3IATLAS is made of. Spectroscopic observations before the disappearance were limited and didn't provide a complete compositional inventory. The comet could be water ice dominated like many solar system comets. It could be carbon monoxide, ice dominated, which sublimates at much lower temperatures and could drive activity at greater distances from the Sunday. It could be rich in silicates and poor in volatiles, more like an asteroid than a typical comet. Each composition would respond differently to solar heating and solar wind interaction. If the nucleus is extremely porous, almost like aerogel, with density barely higher than the gas in the coma itself, thermal waves would penetrate deeply, heating subsurface ice and potentially causing the entire structure to disintegrate in a cascade of sublimation. If the nucleus has an insulating dust mantle covering most of its surface, gas production would be concentrated in a few active areas, creating jets that could spin up the nucleus or torque its rotation in unpredictable ways. If the nucleus is a contact binary too, lumps held together by weak gravity tidal forces and thermal stress could pull it apart. The Sunday in this scenario becomes a kind of cosmic gatekeeper, a destructive force that tests every object passing through the inner solar system. Interstellar comets, having formed in different environments with possibly different structural properties than solar system comets, might be particularly vulnerable, or they might be more robust, forged in conditions that made them tougher. We won't know until we see what emerges. The comparison to Comet Shoemaker-Levy 9 is instructive. That comet was torn apart by tidal forces during a close pass by Jupiter in 1992, breaking into more than 20 fragments that later crashed into the planet in a spectacular series of impacts. The tidal disruption happened because Jupiter's gravity gradient across the comet's diameter exceeded the comet's own self-gravity, literally pulling it apart. The Sunday's tidal forces are much weaker at the distance where 3IATLAS passed, but a comet already weakened by thermal stress or prior fragmentation might succumb to forces that a healthy nucleus would easily resist. Did the Sunday just reveal something terrifying about interstellar visitors? The answer depends on what we see when the comet emerges from conjunction. If 3IATLAS reappears intact, continuing on its hyperbolic trajectory with normal gas and dust production, the solar wind event becomes a footnote, a coincidence that sparked speculation but ultimately meant nothing. If the comet has disintegrated or vanished, we're left with haunting questions. Whether interstellar objects are fundamentally more fragile than our models assume, whether there's something about their formation or structure that makes them vulnerable to solar assault in ways we didn't predict. Part 4. The vigil begins. Astronomers are marking calendars, checking ephemerides, preparing observation plans for the moment when 3IATLAS should become visible again. The timeline depends on several factors, including the comet's exact trajectory, uncertain due to non-gravitational forces, its brightness, which could have changed dramatically, and the observing geometry, which determines how far from the Sunday the comet needs to be before telescopes can detect it against the sky background. Current predictions suggest the comet should emerge from solar conjunction in late October or early November 2025, reaching sufficient solar elongation, the angular separation from the Sunday, as seen from Earth, to be observable with specialized equipment. Initial recovery attempts will likely use space-based observatories, which can block the Sunday's light more effectively than ground-based telescopes. SOHO, the Solar and Heliospheric Observatory, has coronagraphs designed to create artificial eclipses, allowing observation of the region close to the Sunday, where comets often hide. STEREO, the Solar Terrestrial Relations Observatory, consisting of 2 spacecraft in solar orbit, provides different viewing angles that might catch the comet earlier than Earth-based observations. The Parker Solar Probe, humanity's closest messenger to the Sunday, follows an orbit that periodically brings it within the orbit of Mercury, through regions where solar wind speed and temperature reach extreme values. If the probe's trajectory happened to pass near 3IATLAS during the conjunction period, its instruments might have captured data about the comet in conditions no Earth-based telescope can observe. But Parker's science objectives focus on the solar corona and solar wind, not comets. And unless the comet happened to be in the probe's narrow field of view at the right time, we'll have no data from that critical period. Mission scientists have not announced any fortuitous encounters, suggesting the geometry didn't align, or that the comet was too faint for Parker's instruments to detect against the bright solar background. What will the first recovery images show? Best case scenario. The comet appears as expected, perhaps slightly fainter due to dust loss, but otherwise intact, with a visible coma and tail indicating active sublimation of ice from the nucleus. The spectral signature would show familiar lines of water vapor, cyanogen, CN, and carbon monoxide, the molecular fingerprints that confirm comet composition. The tail length and structure would provide information about gas production rates and solar wind conditions in the post-conjunction period. Astronomers would measure the brightness, compare it to pre-conjunction values, and assess whether the comet lost significant mass during its closest approach to the Sunday. Worst-case scenario, nothing appears. The sky remains empty where 3IATLAS should be, suggesting complete disintegration. The nucleus fragmented into pieces too small to detect individually, or vaporized entirely, leaving only a dispersing cloud of gas, too diffused to show up as a distinct object. This outcome would be scientifically disappointing, but not unprecedented. Several comets have disappeared after close solar approaches, and their loss becomes a data point in our understanding of comet fragmentation physics. Between these extremes lie numerous possibilities. The comet could return as multiple fragments. A string of condensations along the orbit, indicating the nucleus split but the pieces survived. Fragment streams are difficult to observe. Each piece is fainter than the original nucleus, but provide valuable information about nuclear structure and breakup mechanics. If 3IATLAS returns as fragments, analysts would measure separation distances and velocities to reconstruct when and how the breakup occurred. Another possibility is dormancy. The comet could have exhausted its near-surface volatiles during the close solar pass, leaving a darkened crust that prevents further sublimation. Until solar heating cracks the crust or erosion exposes fresh ice. Dormant comets look like asteroids, no coma, no tail, just a bare rock reflecting sunlight. If 3IATLAS goes dormant, we'd lose our ability to study its gas composition. But we'd gain insights into surface processes and the formation of insulating mantles. The most intriguing scenario involves unexpected brightening. Sometimes comets fragment in ways that expose fresh, volatile-rich material to sunlight, causing sudden surges in gas production and brightness. A fragmenting nucleus creates new active areas, increasing the total sublimating surface area. If 3IATLAS fragments and brightens simultaneously, the comet that emerges might be more spectacular than the one that disappeared. Though in fragmented form, it would likely fade quickly as small pieces deplete their ice reserves. Spectral diagnostics will be critical. Observations before conjunction showed typical signatures of water and possibly carbon monoxide, but a complete spectral inventory was never obtained. Post-conjunction spectroscopy might reveal species not detected earlier, either because the comet wasn't producing them in significant quantities, or because we weren't observing at the right wavelengths. Oxygen emission lines would indicate water sublimation. CN, cyanogen, points to carbon-nitrogen chemistry. Sodium and iron lines, sometimes seen in comets, could signal exposure of metal-rich material from the nucleus interior. Amateur astronomers have a role to play in the recovery effort. A network of backyard telescopes distributed globally provides continuous sky coverage that professional facilities with limited observing time and fixed schedules cannot match. If 3IATLAS brightens unexpectedly or fragments into widely separated pieces, amateur observers might be the first to notice. Crowdsourced astronomy has grown increasingly important as digital cameras and software let dedicated amateurs produce observations rivaling professional quality. A live cosmic mystery is unfolding in real time, and anyone with a telescope and clear skies can participate. The comet could reappear at any moment, assuming it survived, or days could pass, then weeks, with nothing visible until astronomers reluctantly conclude that 3IATLAS is gone, destroyed by the Sunday it traveled so far to visit. The uncertainty is maddening and exhilarating in equal measure. We sent no probe to intercept the comet. We have no way to actively search for it beyond pointing our telescopes at the predicted location and waiting. All we can do is watch, wonder, and prepare for whatever emerges from the solar glare. A broader question haunts the astronomical community. If the nucleus is gone, do we still have 3IATLAS? Or is it just debris now? A dispersed cloud of dust and gas that once was an interstellar comet, but no longer qualifies as a discrete object. Philosophically, it echoes the ship of Theseus paradox. If every plank of a wooden ship is replaced over time, is it still the same ship? If a comet fragments into 1,000 pieces each, following nearly the same orbit, carrying material from the original nucleus, are they collectively still the comet, or has the comet ceased to exist? There's no formal definition resolving this question. It's a matter of convention and convenience, and different researchers will answer differently depending on their perspective. But the question matters because 3IATLAS represents something precious and irreplaceable, a sample of another star system. Losing it feels like more than just losing an astronomical target. It feels like losing a connection to something vast and distant, a thread linking us to the wider galaxy that was severed before we could fully grasp what we held. Part 5. When coincidence becomes conspiracy. Why does any of this matter beyond the narrow confines of planetary science journals and astronomy conferences? Because humans are pattern-seeking creatures evolved to find meaning in correlation, to see connections even where none exist. And the simultaneous occurrence of a major solar event, the disappearance of an interstellar comet, and multiple large earthquakes on Earth triggered every alarm in our collective unconscious that screams, something is happening. The mainstream scientific position on solar-terrestrial earthquake connections is clear and unambiguous. Earthquakes are driven by plate tectonics, by the slow, inexorable motion of lithospheric plates riding on the convecting mantle, by accumulated strain energy in the crust that eventually exceeds the frictional resistance holding faults locked. Solar activity has no plausible mechanism to trigger this release. Magnetic fields don't affect rock. Solar wind particles don't penetrate to Earth's surface. They're stopped by the magnetosphere and atmosphere. The thermal energy delivered by solar radiation is negligible compared to Earth's internal heat. Every analysis of earthquake catalogs, looking for links to solar cycles or individual solar events, has found nothing more than random coincidence would predict. Yet tantalizing patterns keep appearing in datasets, patterns that don't quite reach statistical significance, but don't quite disappear either. Some researchers working at the margins of respectability continue to explore possible mechanisms. Could ionospheric disturbances caused by solar activity affect the electrical properties of fault zones? Could subtle changes in Earth's rotation rate or magnetic field orientation, driven by solar wind momentum transfer, modulate tectonic stress at levels too small to measure directly, but sufficient to tip a fault already near failure? Could there be magneto-hydrodynamic coupling between the ionosphere and conducting layers in the crust, transmitting energy in ways we don't yet understand? These ideas face enormous skepticism. Extraordinary claims require extraordinary evidence, and the evidence here remains circumstantial at best. But the human mind doesn't operate on statistical significance thresholds. It operates on narrative, on stories that weave disparate events into coherent wholes. When the Sunday attacks, earthquakes strike, and a comet vanishes all in the same news cycle, the story writes itself. Even if the physics doesn't support it, 3IATLAS's interstellar nature adds another layer of mystery and speculation. These objects come from outside our solar system, from environments we barely imagine, formed from materials whose composition and isotopic ratios might differ from solar system norms. They're literally alien in the most precise sense of the word, and humanity has always projected hopes and fears onto the alien and unknown. When One-Eye Oumuamua exhibited acceleration that couldn't be immediately explained by standard comet outgassing, speculation erupted about artificial origins, about alien probes conducting reconnaissance about technologies beyond our understanding. The simplest explanation remained natural processes, but the alien probe hypothesis captured public imagination because it satisfied narrative needs that dry scientific papers about carbon monoxide sublimation could never touch. 3IATLAS disappearing during a solar storm invites similar speculation. Did the comet carry something, a code, that made it a target? Are we witnessing a cosmic quarantine protocol, the Sunday destroying interstellar threats before they can penetrate the inner solar system? These ideas are scientifically absurd, but their psychological appeal is undimmed. We want the universe to hold mysteries deeper than orbital mechanics and spectroscopy. We want hidden meanings behind celestial alignments. We want comets to be more than dirty snowballs. We want them to be messengers carrying information, life, or purpose. The panspermia hypothesis, the idea that life spreads through the cosmos on comets and asteroids, gives these desires a scientific veneer. If comets delivered the organic precursors that led to life on Earth during the heavy bombardment period billions of years ago, then every comet becomes a potential seed carrier. Interstellar comets are especially precious. They might carry chemistry from biospheres around other stars. The destruction of 3IATLAS, if that's what happened, becomes the loss of a biological sample, a library burned before we could read its pages. More exotic possibilities circulate in fringe communities. Electric universe proponents see the Sunday's interaction with the comet as proof of plasma physics they claim mainstream science ignores. They point to the comet's unusual brightness variations, the strong solar wind, and disconnection events in other comets' tails, arguing these phenomena require electrical, not gravitational or thermal explanations. The math of their models rarely withstands scrutiny. Predictions often fail to match observations. But the intuitive appeal of electricity as a universal force. The visual drama of lightning and sparks gives electric universe ideas a persistence that transcends their scientific shortcomings. Conspiracies inevitably emerge. Are space agencies hiding data from the Parker solar probes close passes by the Sunday? Did instruments capture images or spectra of 3IATLAS during the conjunction period? Images officials chose not to release. What would motivate such secrecy? Perhaps the comet exhibited behavior that couldn't be explained, that challenged fundamental assumptions, that frightened those who understood its implications. Perhaps it fragmented in a way inconsistent with natural processes, or emitted signals, or changed trajectory in ways that suggested control. These scenarios are vanishingly unlikely, bordering on impossible. But to minds predisposed to distrust official narratives, absence of evidence becomes evidence of conspiracy. The psychological function of conspiracy theories is well studied. They provide control, or the illusion of control, in the face of random, chaotic events. They replace a universe of meaningless coincidence with one of hidden order and purpose, even if that purpose is malevolent. Better to believe in conspiracies than to accept that earthquakes strike randomly, that comets disintegrate without reason, that we're tiny specks of consciousness on a fragile world hurtling through an indifferent cosmos. The narrative of hidden knowledge and suppressed truth is more emotionally satisfying than the narrative of patient scientific investigation, slowly converging on tentative conclusions. But here's the thing. Sometimes the universe does align in ways that defy probability. Sometimes coincidences are too perfect to dismiss, even when we can't establish causation. The October 2025 confluence of events, solar storm, comet disappearance, earthquakes, might be exactly that. A coincidence so improbable it demands our attention, even if it ultimately means nothing. Or it might be the first hint of connections we don't yet understand, weak couplings between geophysical systems and space weather, operating at levels below our current detection thresholds. Science progresses by investigating anomalies, not by dismissing them. The researchers exploring solar earthquake correlations are doing legitimate, if speculative, science they'll probably find nothing. But the search itself is worthwhile. When 3IATLAS emerges from behind the Sunday, if it emerges, we may not recognize it. The comet that went in might not be the comet that comes out. And when astronomers publish their analyses of what they observe, when they present explanations grounded in physics, chemistry, and orbital mechanics, some people will accept those explanations and move on. Others will keep searching for hidden meanings, for connections between the comet, the earthquakes, and the solar storm that transcend material causation. Both responses are human. Both reflect deep needs to make sense of our place in a cosmos that offers more questions than answers. The Sunday did something terrifying. A comet vanished. The Earth shook. Whatever truth underlies these events, it leaves us with wonder and unease in equal measure. Part 6. The Comet We Can See. While 3IATLAS plays hide and seek behind the Sunday, another comet is putting on a show you can actually watch, assuming you know where to look, and you're willing to wake up before dawn or stay up late after sunset. Comet C 2025-06, discovered by the Mount Lemmon Observatory in Arizona. and thus carrying the nickname Comet Lemmon, is approaching its own close encounter with the Sunday. It's reaching brightness levels that put it within range of binoculars or small telescopes, and possibly even naked eye visibility for observers under dark skies, away from light pollution. The next 2 weeks represent the optimal viewing window. Lemmon's perihelion, its closest approach to the Sunday, is scheduled for mid-November 2025, but the geometry of its orbit brings it to maximum visibility from Earth slightly before perihelion, when it's still far enough from the Sunday's glare to observe comfortably. The comet is currently visible in the pre-dawn eastern sky, rising a few hours before the Sunday. It glows with the soft, fuzzy light characteristic of an active comet, with a well-developed coma and possibly a short tail. Current magnitude forecasts place Lemmon between magnitude 4 and magnitude 5 right, at the threshold of naked eye visibility. The human eye can typically see objects down to magnitude 6 under good conditions, and magnitude 4 should be easily visible away from city lights. Though pinpointing it without binoculars requires knowing exactly where to look. The comet is currently passing through the constellation Cancer, moving eastward against the background stars. Finder charts available online show its path relative to easily recognizable star patterns. Observing comets requires patience and dark skies. Unlike planets, which appear as distinct points or disks, comets are diffuse objects, their light spread across an extended area. This diffuse nature makes them more sensitive to light pollution and sky conditions than compact objects of similar integrated brightness. A magnitude 4 comet will vanish completely in bright suburban skies where magnitude 4 stars remain easily visible. Success requires traveling away from urban areas to locations where the Milky Way is visible overhead, where sky darkness allows your eyes to detect extended, low surface brightness objects. Binoculars are the ideal instrument for comet observing. They provide enough magnification to concentrate the comet's light while maintaining a wide field of view that makes finding and tracking the object easier. 7 by 50 binoculars, a common size owned by many amateur astronomers and nature observers, work particularly well. Mount them on a tripod if possible to eliminate handshake and allow longer viewing periods without fatigue. The comet will appear as a small fuzzy patch, distinctly non-stellar, possibly with a hint of green color from emission by diatomic carbon molecules in the coma. Telescopes can reveal more detail, showing the coma structure, any jets or fans of material emanating from specific active regions on the nucleus, and the tail if one has developed sufficiently. But higher magnification narrows the field of view, making the comet harder to locate initially and harder to keep centered as Earth's rotation carries it across the sky. Many experienced comet observers prefer binoculars for aesthetic reasons. A wide field of view shows the comet in context against starfields and the Milky Way, emphasizing its nature as a temporary visitor moving through more permanent celestial scenery. Early observations of Lemmon revealed something that makes comet scientists nervous and excited in equal measure. Its brightness wasn't following prediction models perfectly. Comets are notoriously difficult to predict because their brightness depends on factors we can't measure directly, like nucleus size, composition, rotation state, surface properties, and dust-to-gas ratio. Models make assumptions about these parameters based on statistics from other comets, but individual comets often deviate from average behavior. Lemmon showed periods where it brightened faster than expected, followed by plateaus where brightness remained nearly constant despite decreasing distance to the Sunday. These deviations could indicate several phenomena: outburst activity, a sudden exposure of fresh, volatile, rich material creates a temporary increase in gas and dust production, causing rapid brightening. Nucleus rotation. If one hemisphere of the nucleus is more active than the other, rotation bringing different hemispheres into sunlight creates periodic brightness variations. More ominously, the deviations could signal the early stages of fragmentation, where the nucleus begins to break apart under thermal or tidal stress. Fragmentation is the hidden danger that haunts every comet prediction. A comet can be brightening, normally following its expected curve toward perihelion, looking healthy in every respect, and then suddenly start to come apart. The process can be rapid or gradual. Sometimes a large chunk splits off and forms a separate condensation visible near the main nucleus. Sometimes the entire nucleus disintegrates into a cloud of small fragments, individually too faint to see, but collectively able to create a dramatic increase in total brightness as their combined surface area drives enhanced sublimation. The physics of fragmentation involves mechanical strength, thermal stress, and spin state. Comet nuclei are weak structures, more like compacted snow than solid rock, held together primarily by their own feeble gravity, supplemented by tensile strength from icing and possibly organic tars. When the Sunday heats one side of the nucleus, thermal expansion creates stress. If the nucleus is spinning, centrifugal forces add mechanical stress, and jets create torques that can spin the nucleus up to faster rotation rates. At some point, accumulated stress exceeds material strength, cracks propagate, and the nucleus splits. Lemmon's sublimation science adds another layer of complexity. The comet appears to be driven by carbon monoxide or carbon dioxide sublimation, as much as or more than water sublimation. These molecules are more volatile than water, meaning they turn from solid to gas at lower temperatures and greater distances from the Sunday. A carbon monoxide-driven comet can be active far beyond the snow line, where water ice remains frozen, producing a coma and tail while still in the outer solar system. As the comet approaches perihelion and temperatures rise, water sublimation eventually takes over, often creating a transition in activity patterns and brightness behavior. Tail interactions with the solar wind provide another observational opportunity. Lemmon's ion tail, if it develops one, will point directly away from the Sunday, blown by the solar wind like a windsock. The dust tail follows a curved path, particles pushed by solar radiation pressure, but retaining the orbital motion they had when released from the nucleus. These two tail types, ion and dust, often separate into distinct structures visible in photographs. The ion tail appears bluish from carbon monoxide ion emission strite, and sometimes featuring streamers or knots caused by magnetic field irregularities in the solar wind. The dust tail appears yellowish, white from reflected sunlight, broader, more diffuse, curving gently away from the nucleus. Comparing Lemmon to 3IATLAS highlights fundamental differences between solar system native comets and interstellar visitors. Lemmon formed 46 billion years ago in the disk of gas and dust surrounding the young Sunday, probably in the region beyond Neptune, where temperatures were cold enough for water and other volatiles to condense as ice. Gravitational perturbations from the giant planets eventually scattered it into the Oort cloud, that vast spherical reservoir of comets surrounding the solar system at distances up to 100,000 astronomical units. Something, perhaps the gravitational influence of a passing star or a giant molecular cloud, perturbed Lemmon's orbit, sending it falling back toward the Sunday on the journey we're now observing. Its composition reflects primordial solar system chemistry. The isotope ratios and molecular abundances present in our local region of the galaxy 4 billion years ago. 3IATLAS formed somewhere else, around a different star in conditions that might have been similar or radically different. The temperature and pressure in that protoplanetary disk, the abundance of heavy elements, the radiation environment, the timing of planet formation, all these factors influence comet composition and structure. By comparing interstellar comets to solar system comets, we're essentially comparing samples from different stellar nurseries, looking for commonalities that reveal universal processes and differences that highlight local variations. Lemmon serves as a real-time reminder of how fragile comets are. Every comet is a gamble against disintegration. Most survive their perihelion passage, lose some mass to sublimation, retreat back to the outer solar system, or beyond, and remain intact. Some fragment dramatically, providing spectacular shows as multiple nuclei and expanding dust clouds brighten and fade. A few vanish completely destroyed so thoroughly that tracking them afterward becomes impossible. Watching Lemmon during its peak visibility window isn't just about appreciating a beautiful celestial sight, it's about witnessing a survivor, an object that has endured billions of years in the deep freeze of the Oort cloud, and is now running a gauntlet of solar heat and radiation that might or might not end in its destruction. The timing is fortuitous. While 3IATLAS hides behind the Sunday, Lemmon provides a substitute target, a different comet we can actually observe and study. If you haven't seen a comet with your own eyes, if you've only encountered them as images on screens or diagrams in textbooks, now is your chance. Go outside before dawn, find a dark location, let your eyes adapt for 10 or 15 minutes, and scan the eastern sky in Cancer, that fuzzy patch of light. If you find it contains ice that formed before Earth existed, organic molecules that predate life, and silicate dust older than our planet, you're seeing a messenger from the beginning of the solar system, and in 2 weeks it will fade from view. Its brief moment of visibility is over. Its destiny, survival, or disintegration is still unwritten. Watch the skies now while Atlas hides Part 7. The Swan and the context. Comets have a funny way of showing up in groups, or at least that's how it seems to observers tracking these icy visitors. The reality is more straightforward. At any given time, countless comets orbit the Sunday at various distances. Most are too faint to spot without large telescopes. A few grow bright enough to catch amateur attention, and very rarely one shines bright enough to be seen with the naked eye and enter public consciousness. The clusters, we notice, come from a mix of observational bias and the random nature of comet discoveries, but they still create periods when comet watchers have multiple targets to choose from. 2025 is shaping up to be one of those years. Alongside Lemmon and the vanished 3IATLAS, another comet designated C2025R2 Swan has joined the catalogue. Swan doesn't refer to the constellation. It comes from the Solar Wind Anisotropies instrument aboard the SOHO spacecraft. This instrument scans the sky in ultraviolet, UV wavelength sensitive to hydrogen emission, and comets produce enormous clouds of hydrogen. These clouds form when solar UV radiation splits water molecules apart, creating neutral hydrogen atoms. The atoms are invisible to optical telescopes, but they glow brightly in specific UV wavelengths, allowing Swan to detect comets months before ground. Based observers can spot them. CC2025R2 Swan was first found by its hydrogen corona, that huge, invisible cloud surrounding its visible coma. Follow-up optical observations confirmed the discovery and let astronomers calculate its orbit. It's following a long, stretched elliptical path that will bring it to perihelion, its closest approach to the Sunday in early 2026. Well after Lemmon's close pass, but soon enough to keep comet enthusiasts, who've already prepped their gear and plans, excited. Early brightness estimates suggest Swan might reach magnitude 6 or 7 at perihelion. That puts it in binocular range, but it will likely stay too faint for naked eye, viewing except under exceptionally dark skies. The predictions are shaky though. They depend on two unknowns: the nuclear size and activity level. Some comets discovered by the Swan instrument have far exceeded brightness expectations as they near the Sunday. Others have disappointed, staying faint and diffuse despite hopeful forecasts. The only way to know for sure is to watch and wait. An intriguing possibility with new comets is meteor showers. When a comet approaches the Sunday, it sheds dust that spreads along its orbit, creating a stream of particles. If Earth's orbit crosses this stream, the particles slam into our atmosphere at high speeds, typically 30 to 70 kilometers per second, and vaporize in bright streaks we call meteors or shooting stars. Most annual meteor showers we see, like August's Perseids or December's Geminids, come from Earth passing through well-established dust trails. These trails are left by comets that have made multiple perihelion passes, depositing dust over centuries or millennia. But new comets, making their first trip through the inner solar system, can trigger unpredictable meteor activity. Their dust isn't smoothed out by repeated passes or planetary tugs. Dense clumps of particles might form. If Earth happens to plow through one of these clumps, meteor rates can spike dramatically, creating a meteor storm with hundreds or thousands of visible meteors per H-hour. These events are rare and hard to predict. We can't directly measure how dust is spread along the comet's orbit. In the coming months, astronomers will map Swan's orbit precisely to see if Earth might intersect any of its dust streams. Even a low chance of a meteor shower gets comet and meteor fans excited. Watching a meteor storm is a bucket list experience, a celestial fireworks show that happens maybe once or twice per generation. During a storm, all meteors appear to radiate from a single point in the sky, called the radiant, an illusion from parallel particle trajectories entering the atmosphere. The whole sky seems to rain meteors, with bright streaks in every direction. It's a sensory overload that photos can never fully capture, but for every comet that shines bright and delivers, several fizzle out. Comet astronomy is full of failed predictions, objects hyped as great comets, that end up faint and unremarkable. Comet Kowatek in 1973 was predicted to be one of the century's brightest comets, but it barely reached naked eye visibility, disappointing millions who'd waited for a spectacular show. Comet Ison in 2013 was supposed to survive perihelion and glow brilliantly. Instead, it disintegrated. These failures teach humility. They remind us how little we still understand about comet physics. Comparing Swan's and Lemmon's brightness curves will eventually yield useful science. Observing two comets at the same time, under similar solar conditions, lets us directly compare their activity levels and sublimation physics. Differences in brightness at the same distance from the Sun hint at differences in nucleus size, composition, or surface properties. If one comet is water-dominated and the other carbon monoxide-dominated, their activity patterns will diverge in telltale ways. If one fragments and the other doesn't, we'll get clues about structural differences that make comets more or less likely to break apart. Pitting Swan and Lemmon against each other also creates a tense question. If so many comets fail, will 3IATLAS fail too? Is there something about the current solar environment that makes comet survival less likely? The October 2025 coronal hole event could have been a one-time fluke, or it could signal a period of stronger solar activity that threatens any comet passing through the inner solar system. The Sunday's 11-year activity cycle is heading toward solar maximum, a time when sunspots and coronal mass ejections become more frequent and solar wind speeds and magnetic field strength increase. Comets that reach perihelion during solar maximum face harsher conditions than those that arrive during solar minimum. The history of comet fragmentation paints a sobering picture. Comet Shoemaker-Levy 9 was torn apart by Jupiter's tidal forces in 1992. Its fragments crashed into the planet in a spectacular series of impacts in 1994, showing just how thoroughly a comet can be destroyed. Comet 73 P-Watchman. Watchman 3 fragmented during its 1995 appearance, splitting into multiple pieces that drifted apart over the years. By its 2011 return, it had broken into more than 60 identified fragments, with a debris field stretching thousands of kilometers along its orbit. Some fragments stayed active, forming small comas. Others went dormant, their volatiles depleted or sealed under inactive crusts. These fragmentation events matter for predicting space hazards. A single large comet nucleus poses minimal risk to Earth. The chance of a few kilometer-wide nucleus hitting our planet is vanishingly small. But a fragmenting comet creates dozens or hundreds of pieces, each capable of entering our atmosphere. While individual fragments are smaller and less destructive than the original nucleus, the odds that one crosses Earth's path go up. Most comet fragments burn up harmlessly in the atmosphere or miss Earth entirely, but the risk calculation changes when you're dealing with scattered debris instead of a single object. Looking ahead to future comets, like the one hyped as the century's brightest for years to come, puts our current observations in perspective. Comets are the solar system's chaotic clock. They appear unpredictably, brighten erratically, and break apart without warning. They mark time in human memory differently than the steady motions of planets and stars. One generation remembers Halley's Comet in 1986, a letdown for most, but culturally significant. The generation before remembers Comet Hale-Bopp in 1997, visible to the naked eye for months, bright enough to spot from city centers. The current generation might remember Lemmon, Swan, or 3IATLAS, if any of them survive and shine bright enough. Are we really in a cluster of unusual comet appearances? Statistical analysis of comet discovery rates over decades shows fluctuations. These could mean real clusters, or they could just reflect better detection technology. More telescopes scanning more sky with greater sensitivity naturally find more comets. The Atlas survey that found 3IATLAS was built to spot near-Earth asteroids. Comets are a bonus. The Catalina Sky Survey, Mount Lemmon Observatory, PAN, stars in Hawaii, all these automated systems watch constantly for anything that moves, and since comets move, they get found. But there's a tantalizing hint in the data. The Oort cloud, the distant reservoir of comets, might get jostled, sending showers of comets falling toward the inner solar system, passing stars. Gravitational tugs from giant molecular clouds in the galaxy, even the solar system's up and down motion through the galactic plane as it orbits the Milky Way's center could shake comets loose. If real, these comet showers happen on timescales of millions of years, far too long for humans to observe directly. But buried in Earth's geological record, evidence of clustered impact craters might reveal ancient comet storms that battered the inner solar system during the age of dinosaurs, or even earlier in Earth's history. Comets are the solar system's chaotic clock, precisely because they don't follow the regular, predictable paths of planets. Most planets orbit in nearly circular paths, Their positions can be calculated centuries in advance with high precision. Comets come from the outer dark on highly elliptical orbits. Their return times, if they return at all, span decades, centuries, or millennia. Some are new visitors making their first trip from the Oort cloud. Others are short-period comets, trapped by Jupiter's gravity into orbits that bring them back every few years. They remind us the solar system isn't a clockwork machine of perfect orbits. It's a dynamic, chaotic place where gravitational interactions constantly shuffle trajectories and new players step onto the stage without warning. Part 8. The Unbreakable Signal. While astronomers scan the skies for comets and track solar wind, another kind of cosmic race unfolds in laboratories and ground stations here on Earth. In 2025, China announced the completion of the world's longest quantum communication link, a 12,900-kilometer network connecting Beijing to distant ground stations through satellite relays, and claimed the system provides effectively unhackable data transmission. This announcement represents a milestone in the quantum information revolution. And if the system works as advertised, it changes the landscape of global communications and cybersecurity in ways that extend far beyond immediate military or commercial applications. Quantum key distribution, QKD, the underlying technology, exploits fundamental properties of quantum mechanics to detect eavesdropping. The basic principle is elegant and strange in equal measure. Information is encoded in the quantum states of photons, single particles of light, transmitted through optical fibers or through the space between satellites and ground stations. The quantum no-cloning theorem guarantees these states cannot be copied perfectly. Any attempt to measure or intercept the photons necessarily disturbs them in detectable ways. This means two parties sharing a quantum communication channel can generate encryption keys and know with certainty whether anyone tried to intercept those keys during transmission. The process begins with entangled photons, pairs of particles created simultaneously, sharing a quantum connection such that measuring properties of one photon instantly affects the other, regardless of the distance separating them. This phenomenon, which Einstein famously called spooky action at a distance, has been verified in countless experiments and forms the basis for several proposed quantum technologies, including quantum computing and quantum teleportation. For quantum key distribution, entangled photons allow two parties to establish shared random numbers that can be used as encryption keys. Hardware implementation requires extraordinary precision. Photons must be generated, entangled, transmitted, and detected with minimal loss and maximal fidelity. Optical systems must align satellite transceivers with ground stations across hundreds or thousands of kilometers, while compensating for atmospheric turbulence, satellite motion, and Earth's rotation. Single photon detectors must register individual particles, arriving at rates of thousands or millions per second, distinguishing real signals from background noise and detector dark counts, false triggers with no photons present. Error correction protocols must account for inevitable imperfections while still guaranteeing security. China's system uses the Meisha satellite, launched in 2016 and named after an ancient Chinese philosopher. The satellite orbits at roughly 500 kilometers altitude, passing over ground stations in a sun-synchronous orbit that provides regular communication windows during each pass, lasting several minutes. The satellite distributes entangled photons to pairs of ground stations, allowing them to establish shared encryption keys. These keys then secure conventional data transmission using standard encryption algorithms, with the quantum channel guaranteeing the keys themselves were not compromised. The recent expansion to 12,900 kilometers represents a significant engineering achievement. Earlier demonstrations covered shorter distances or relied on trusted relay stations that could theoretically be compromised. The new system chains quantum links across multiple satellite passes and ground stations, creating end-to-end security across continental scales. According to Chinese researchers, the network already serves government and financial institutions, protecting communications against both current and future decryption threats. That last point matters crucially. Current encryption systems, those protecting everything from bank transactions to classified government communications, rely on mathematical problems that are computationally difficult to solve with classical computers, e.g., factoring large numbers, computing discrete logarithms. These tasks require so much computational time that breaking encryption becomes impractical even with the fastest supercomputers available. But quantum computers, if built at sufficient scale, could solve these problems efficiently, rendering current encryption obsolete. Data encrypted today and captured by adversaries could be decrypted years or decades in the future. Once quantum computers mature, quantum key distribution offers protection against this harvest now, decrypt later threat because its security does not rely on computational difficulty. It relies on fundamental physics. Western nations, particularly the United States and European countries, view China's progress in quantum communications with concern. The 2025 MIT Technology Review Quantum Index ranks China ahead in several quantum technology metrics, including quantum communications and quantum sensing. American research programs are working to catch up. The Department of Energy funds quantum network testbeds, and DARPA explores space-based quantum communication architectures. But China's early lead and substantial government investment have created a quantum gap that worries defense planners and technology strategists. The policy implications extend beyond simple technological competition. If quantum communication networks become the backbone of future secure communications, nations without access to the technology face potential information disadvantage. International agreements governing quantum technology development remain non-existent. Questions about export controls, technology transfer, and standardization remain unresolved. Some researchers advocate for open collaboration and shared development of quantum networks as global infrastructure, similar to how the Internet developed as an international resource. Others push for competitive advantage and restricted access, viewing quantum superiority as a strategic asset too valuable to share. Could space-based quantum networks become the backbone of the future Internet? The vision involves constellations of quantum satellites providing global coverage, ground stations in every major city, and quantum repeaters extending range beyond direct line of sight limits. Data would travel encrypted by quantum keys that refresh continuously, immune to interception, resistant even to future technologies we haven't yet imagined. The system would integrate with existing fiber optic networks, creating a hybrid classical quantum infrastructure where quantum channels distribute keys and classical channels carry bulk data. Conspiracies naturally emerge around technologies this advanced, and this secret quantum key distribution systems require extensive testing and calibration, generating data about photon transmission statistics, detector efficiency, and error rates. Most of this data remains classified or proprietary. Chinese publications describe the system's capabilities in general terms, but omit engineering details that would allow independent verification or replication. Western intelligence agencies undoubtedly monitor the program closely, using signals intelligence and other means to assess its actual capabilities versus public claims. This opacity feeds speculation. Does the system work as advertised? Do vulnerabilities exist that aren't being disclosed? Some worry about state surveillance potential. A government controlling a nationwide quantum communication network has unprecedented ability to monitor who communicates with whom, even if the content remains encrypted. Metadata, information about communication patterns, not content, often reveals as much as the messages themselves. Traffic analysis can identify social networks, track movements, predict behavior. A quantum network that logs every connection, every photon transmission, every key generation event creates a surveillance infrastructure of staggering scope. The tie-in to the 3IATLAS narrative rests on an interesting parallel. Just as comets carry messages from other star systems, encoded not in language but in chemistry and isotope ratios, humans now build systems to carry unbreakable encoded messages across our own planet. Both represent information that survives hostile environments. Comet chemistry surviving interstellar space and solar heat. Quantum keys surviving active adversaries trying to intercept them. Both push the boundaries of what's possible. Comets as natural information carriers shaped by billions of years of physics. Quantum networks as artificial information carriers shaped by decades of engineering. Unknowns remain numerous. Current quantum key distribution rates, typically measured in kilobits per second, lag far behind classical communication speeds, measured in gigabits or terabits per second. Scaling quantum networks to handle internet-level traffic requires either dramatic improvements in photon transmission and detection efficiency or fundamentally new approaches to quantum networking. Decoherence, the loss of quantum properties due to environmental interactions, places fundamental limits on how long quantum states can be maintained and how far they can be transmitted. Satellites help extend range by operating in the vacuum of space, above most of the atmosphere, but atmospheric turbulence at ground stations still degrades performance. Endpoint security presents another challenge. Quantum key distribution guarantees secure key transmission, but the keys must ultimately be used by classical computers to encrypt and decrypt data. If those computers are compromised through malware, physical access, or side channel attacks that monitor electromagnetic emissions or power consumption, the unbreakable quantum keys become irrelevant. Security is only as strong as the weakest link, and in any real system, weak links proliferate. The quantum space race narrative captures something true about human nature and technological development. We compete even in understanding and harnessing the fundamental laws of physics. Quantum mechanics, arguably the most successful physical theory ever developed in terms of predictive accuracy and technological impact, has become a weapon in geopolitical competition. The same quantum principles that explain atomic structure and chemical bonds now secure communications and promise revolutionary computing power. Nations invest billions in quantum research, not out of pure scientific curiosity, but because quantum technology might determine military balance and economic leadership in the coming decades. Whether this competition drives innovation faster than collaboration would, whether the benefits of quantum networks will be shared globally or concentrated in a few technologically advanced nations, these questions remain unanswered as the race accelerates. Part 9. The circular economy inside you. Science occasionally produces discoveries so unexpected, so contrary to intuition, that they force us to reconsider fundamental assumptions about what's possible. The announcement that synthetic biologists have engineered yeast to convert human urine into the bone mineral hydroxyapatite represents one of those breakthroughs. Its potential applications range from medical to ecological, and its deeper implications touch on questions of waste value and the surprising ways biological systems can be reprogrammed to transform one substance into something entirely different and useful. Urea. Urea, the primary nitrogen containing component of urine, is a waste product of mammalian metabolism. When proteins break down in the body, amino acids are metabolized, and the nitrogen they contain must be excreted. Aquatic animals release ammonia directly, a simple, energy-efficient solution when you live in water that dilutes and carries away the toxic compound. Land animals face a dilemma, though. Ammonia is too toxic to accumulate, but water conservation matters. So terrestrial animals evolved more complex solutions. Birds and reptiles produce uric acid, a relatively insoluble compound that precipitates out and can be excreted as a paste, minimizing water loss, while mammals produce urea, soluble enough to transport in water, but far less toxic than ammonia, excreted in liquid urine as a compromise between water conservation and waste removal. Humans produce roughly 1 to 2 liters of urine daily, depending on fluid intake and metabolic rate, containing about 20 to 30 grams of urea. That's roughly 10 kilograms of urea per person per year, multiplied by 8 billion people globally, totaling roughly 80 million metric tons of urea excreted annually. Today, this urea ends up in sewage systems, gets broken down by bacteria, or is released into the environment. The new synthetic biology approach asks, could this waste stream be converted into something valuable? Hydroxyapatite is the mineral component of bones and teeth, a calcium phosphate compound with the formula TOTI-POR. It provides the hardness and structural integrity that lets bones support body weight and protect organs. Natural bone is a composite material, hydroxyapatite crystals embedded in a collagen protein matrix, combining the hardness of mineral with the flexibility and toughness of organic fibers. Medical applications demand pure hydroxyapatite for bone grafts, dental implants, and reconstructive surgery. Currently, hydroxyapatite is either synthesized through chemical processes or harvested from animal bones. Both methods have limitations in purity, crystal structure, and production cost. The engineered yeast approach works through metabolic pathway engineering. Researchers identified the series of enzymatic reactions needed to convert urea into hydroxyapatite's chemical precursors, then inserted genes encoding those enzymes into yeast cells. The result, Saccharomyces cerevisiae, ordinary baker's and brewer's yeast, now contain synthetic metabolic pathways that do not exist in nature. When fed urine as a nitrogen source and supplied with calcium and phosphate ions, the yeast cells produce hydroxyapatite crystals that precipitate out for collection. The mechanism involves multiple steps. First, the enzyme urease breaks urea into ammonia and carbon dioxide. The ammonia is integrated into amino acid synthesis pathways, while the carbon dioxide reacts with added calcium and phosphate ions in mineralization reactions that form hydroxyapatite. The precise crystallography of the product, the size, shape, and purity of the hydroxyapatite crystals depends on reaction conditions including pH, temperature, and ion concentration, and the genetic programming of the yeast's pathways. Early results show promise. The hydroxyapatite produced has properties similar to natural bone mineral, but significant optimization remains before the process becomes practical for medical use. Current efficiency and yield rates limit immediate applications. The yeast produces hydroxyapatite at concentrations too low for commercial viability, requiring large bioreactor volumes to generate meaningful quantities. Purification is another challenge. The hydroxyapatite must be separated from yeast cells, growth medium components, and metabolic byproducts. Purity is critical for medical use. Foreign proteins or bacterial endotoxins in implanted hydroxyapatite could trigger immune responses or infections. Achieving medical-grade purity from a biological production system demands rigorous quality control and purification protocols. Nevertheless, the transformative potential is clear. Millions of people experience bone fractures annually. While most heal naturally, complex fractures or bone loss from disease or trauma often require grafts or synthetic materials to support healing. Current bone graft options include autografts harvested from the patient's own body, allografts from cadavers, and synthetic ceramics, each with drawbacks. Autografts require additional surgery to harvest tissue. Allografts carry small risks of disease transmission and immune rejection. Synthetic ceramics sometimes fail to integrate well with natural bone. If production and purification challenges are solved, hydroxyapatite biologically synthesized from waste could offer an abundant cost-effective alternative. Dental implants represent another major market. Hydroxyapatite coatings on titanium implants improve osseointegration, the bonding between the implant and jawbone. Current coatings use hydroxyapatite produced via energy-intensive high-temperature chemical processes. Biologically produced hydroxyapatite, made at room temperature in aqueous solutions, would reduce energy use and carbon footprint, while potentially creating more bone-like crystal structures that integrate better with living tissue. The ecological benefits extend beyond direct material use. Urea in wastewater contributes to eutrophication when released into rivers and coastal waters. Excess nitrogen stimulates algal growth, leading to blooms that deplete oxygen and create dead zones, areas where no aquatic life can survive. Capturing urea and converting it into solid mineral removes nitrogen from the waste stream, reducing environmental harm. This is waste valorization, treating waste as a resource rather than a disposal problem. Controversies naturally arise around using human waste in medical materials. Cultural taboos around urine and feces run deep even when we intellectually understand that purified compounds bear no memory of their origin. The calcium atoms in urine-derived hydroxyapatite are identical to those from any other source, once purified. The material carries no trace of its waste origins beyond the historical fact of its production pathway. Yet psychological resistance remains. Would patients accept bone grafts or dental implants made from urine? Would regulatory agencies approve such materials for human use? These questions hinge more on cultural values and risk perception than technical feasibility. Astronaut applications offer perhaps the most compelling use case. Mars colonists or crew on long-duration space missions face severe resource constraints. Every recycling opportunity is valuable. Crew members produce urine daily, and that urine contains nitrogen and other elements that must be processed, either recycled or discarded. Converting urine into usable hydroxyapatite for medical or structural use kills two birds with one stone. managing waste while producing a useful product. The closed-loop life support systems needed for space exploration push designers toward maximum recycling and minimal waste. Your waste could literally save your life on Mars if a bone fracture requires a graft, and the only available hydroxyapatite was produced from crew urine. Big Pharma resistance to circular biotech adoption is a predicted, not yet demonstrated conspiracy, but it follows logical lines. Pharmaceutical and medical device companies profit from existing production methods and supply chains. Disruptive technologies that threaten established business models often face resistance, regardless of their technical merit. Whether this resistance emerges depends on factors including production costs, scalability, regulatory pathways, and intellectual property landscapes. If the technology can be patented and controlled by industry leaders, adoption is more likely. If it threatens to commoditize a high-margin product, resistance is more likely. The deeper takeaway transcends the specific urine-to-bone application. Nature wastes nothing. Nutrients cycle through ecosystems. One organism's waste becomes another's food. Energy flows and elements circulate. Early human cultures had simpler waste management. Low population densities meant natural processes could degrade and recycle most waste. Industrialization and urbanization broke these cycles, creating waste streams that overwhelm natural recycling capacity. Synthetic biology gives us tools to rebuild those cycles, artificially engineering organisms to fill ecological niches that don't exist in nature, but serve human needs. Converting urine to bone mineral is just one example. The same principles apply to turning carbon dioxide into fuel, plastic waste into biodegradable polymers, and agricultural runoff into valuable chemicals. We're learning to close the loops our technological development opened, catching up to the circular economy nature perfected over billions of years. Part 10. The yawn that crosses species. Animal behavior fascinates us endlessly. It reflects cognitive and emotional states we recognize from our own lives, yet unfolds in creatures whose minds remain alien to us. Contagious yawning. The phenomenon where seeing someone yawn triggers an irresistible urge to yawn yourself was, until recently, thought to exist only in humans and a handful of highly social mammals, chimpanzees, dogs, and a few others. But a study documenting contagious yawning in zebrafish has upended that assumption, raising puzzling questions about the behavior's evolutionary origins and neural mechanisms. Zebrafish, small freshwater fish native to South Asian rivers, popular in both scientific research and home aquariums, are workhorse model organisms for studying vertebrate development and behavior. Their embryos are transparent, letting researchers watch organs form in real time under microscopes. Their genetics are well mapped, with tools to edit genes and observe the results. They're small, cheap to care for, and produce hundreds of offspring at a time, ideal for large-scale experiments. But no one expected them to yawn contagiously. The experimental setup was straightforward. Researchers placed zebrafish in adjacent tanks with transparent walls so the fish could see each other. They induced yawning in one fish via oxygen deprivation, a known trigger for yawning in many species. Cameras recorded both the yawning fish and the observer fish. The analysis revealed a clear pattern. Observer fish yawned significantly more often after watching their neighbor yawn. The timing correlation suggested genuine contagion, not coincidental yawning triggered by shared environmental cues. Why is this so shocking? Contagious yawning was thought to require mirror neurons or similar neural circuits, brain systems that let an animal mentally simulate another's actions and states. These circuits are concentrated in primate brains and suspected in some social mammals and form the basis for empathy, imitation learning, and theory of mind, understanding others' mental states. But zebrafish lack the cortical structures where mammalian mirror neurons live. Their neural organization is fundamentally different, simpler, in some key ways though by no means simple overall. The presence of contagious yawning in zebrafish suggests one of two possibilities. Either the behavior doesn't need the sophisticated neural machinery we assumed, or convergent evolution, the independent development of similar traits in unrelated species, created functional, yawning circuits in fish via entirely different anatomical paths. No species' neural circuits for yawning are fully understood. Yawning itself is a coordinated sequence. Muscles in the jaw, face, throat, and respiratory system contract, opening the mouth wide for a deep inhale, followed by a slow exhale, once triggered. It's involuntary hard to suppress, even in social situations where yawning is considered rude. Triggers are diverse: fatigue, boredom, low oxygen, or the sight of others yawning. This multiple triggers pattern implies overlapping neural pathways that all feed into the same motor response. In humans, contagious yawning ramps up during childhood, peaks in young adulthood, and correlates with empathy. People who score high on empathy tests yawn more readily when they see others yawn. Individuals with autism spectrum disorders, who often struggle with social cognition and empathy, show less contagious yawning. These links supported the hypothesis that contagious yawning relies on brain systems for social connection and emotional resonance. Finding the behavior in zebrafish creatures we don't associate with empathy or complex social thought breaks that neat narrative. The evolutionary mystery deepens when we look at the behavior's taxonomic distribution. It exists in humans, chimpanzees, bonobos, dogs, and now zebrafish. But it's absent or unproven in many tested species: cats, horses, most birds. This scattered pattern across the animal kingdom has two possible explanations. Either contagious yawning evolved independently multiple times, or it originated in a very ancient ancestor and was later lost in most lineages. Neither is fully satisfying. Convergent evolution of something as specific as contagious yawning in mammals and fish seems unlikely, unless the behavior serves a critical function we're missing. An ancient origin leaves us wondering why so many species abandoned it. Hypotheses about its function vary widely. One idea is group coordination. Contagious yawning syncs a group's arousal or attention. If one animal yawns in response to environmental change, say a shift from alertness to rest, the contagious signal helps the whole group coordinate behavior. Fish schools need precise coordination. They move as a unit, turn simultaneously, maintain tight spacing, and evade threats in sync. Could contagious yawning be part of that coordination toolkit? Another hypothesis focuses on stress relief and social bonding. Yawning might regulate stress hormones or reset neural states during social tension. Seeing others yawn and responding could create a feedback loop that eases group-wide stress. Zebrafish are social in the wild. They school, form dominance hierarchies, compete for mates, and watch for predators. Contagious yawning might help keep the group cohesive under pressure. Controversy lingers over whether the zebrafish behavior is true yawning or just a misclassified jaw movement, like gill-related actions. Fish don't breathe air normally, so the respiratory part of mammalian yawning has no direct equivalent. Critics argue that calling it contagious yawning is anthropomorphism, projecting human traits onto a superficially similar but functionally different fish behavior. Without proof it shares mammals' neural triggers or physiological effects, proponents push back. The zebrafish behavior shares key features of mammalian yawning. It's involuntary, has a fixed, stereotyped motor pattern, is triggered by low oxygen, and now shows social contagion. The neural pathways may differ, separated by hundreds of millions of years of evolution, but if the behavior serves similar purposes and responds to similar cues, yawning is a legitimate label. Biology is full of convergent evolution. Bird wings and bat wings are anatomically different but functionally identical. Maybe fish yawning and mammalian yawning are convergent solutions to the same behavioral or physiological challenges. Speculation extends to deeper biological questions. Could contagious yawning be a universal signal, an ancient communication system that predates complex social cognition? Maybe the basic neural circuits for contagious yawning evolved early in vertebrate history and were preserved for hundreds of millions of years, because they gave social species a survival or reproductive edge, enough to offset the cost of maintaining the neural machinery. A fringe idea, rarely spoken in formal academic settings, but whispered in conference halls, asks if synchronization phenomena might extend beyond single species, even across entire branches of life. Contagious yawning, as we know it, works via sensory input. Seeing or hearing a yawn triggers neural pathways that produce a yawn. But nature is full of synchronization. We're only beginning to understand. Heart cells in a petri dish sync their beats via electrical and chemical signals. Fireflies in Southeast Asian mangroves sync their flashes across hundreds of individuals. Could there be deep biological principles of synchrony and resonance that manifest in contagious yawning and beyond? The link to cosmic themes lies in synchronization across scales. Fish schools move as coordinated units, responding to each other's movements via lateral line sensors, which detect water pressure changes. Bird flocks turn in unison, each individual following simple rules about spacing and alignment to create complex emergent patterns. On larger scales, planets orbit in resonances. Gravitational interactions lock their orbits into integer ratios. Jupiter's moons Europa, Ganymede, and Io orbit in a 4:2:1 resonance, repeating their positions in a cycle. At cosmic scales, galaxy clusters move under mutual gravity, their dynamics linked across millions of light-years. Synchronization appears to be a fundamental principle that organizes systems from the molecular to the cosmic. Oscillators, whether neurons firing, hearts beating, pendulums swinging, or planets orbiting, tend to phase lock when connected, their rhythms aligning to a common frequency. The math of coupled oscillators reveals surprising similarities across wildly different physical systems. Maybe contagious yawning is a biological example of these universal synchronization rules. A social oscillator that couples via observation and triggers phase-locked responses. Human brains and stars might have more in common than we think, if we shift our perspective from specific mechanisms to abstract principles. Both are complex dynamical systems with internal structure, emergent traits, and connections to their environments. Both process information, though in radically different ways, at vastly different scales. Brains process sensory input and generate behavior via electrochemical signals in neural networks. Stars process gravitational input and generate radiation via nuclear fusion regulated by hydrostatic and thermal balance. The analogy breaks down if stretched too far, but it points to big questions about complexity, information, and order in the universe. At its core, the zebrafish study reminds us how little we truly understand animal minds and behaviors. Every assumption, every proven fact about what animals can or can't do, is temporary, ready to be revised when new evidence emerges. We thought contagious yawning needed empathy and mirror neurons. Zebrafish apparently didn't get that memo. How many other behaviors we call uniquely human or uniquely mammalian might have deeper roots or wider distribution than we realize? Tool use. It exists in birds and octopuses. Culture-learned behaviors passed socially across generations. It exists in whales and crows. Metacognition. Thinking about thinking. Hints of it exist in rats and dolphins. The more we look, the more the lines we draw between humans and other animals, between complex and simple minds, blur under scrutiny. Part 11. The stone that will skim Earth's atmosphere. April 13th, 2029 will be a date humanity remembers. Assuming we're still here to remember things, on that day, asteroid 99942 Apophis, named for the ancient Egyptian demon of chaos and darkness, will pass Earth at a distance of 31,000 kilometers. To put that in perspective, geostationary satellites orbit at roughly 35,000 kilometers. Apophis will pass inside the ring of satellites that provide weather forecasting, communications, and GPS navigation. It will be visible to the naked eye, a point of light moving rapidly against the stars. The first time in recorded history that an asteroid of this size has come so close to Earth that casual observers can watch it pass. Current orbital calculations show no impact risk. The close approach is certain, the geometry well understood, but the trajectory will carry Apophis safely past our planet without collision. This certainty represents decades of careful observation and orbital refinement. When Apophis was discovered in 2004, initial trajectory calculations couldn't rule out a small but non-zero probability of impact during its 2029 pass. The announcement triggered brief public alarm and intense scientific interest. Subsequent observations as the asteroid appeared in different parts of its orbit refined the calculations, shrinking the uncertainty ellipse, the region where the asteroid might be at any given time, until the 2029 impact possibility was ruled out completely. But the story doesn't end in 2029. The close pass will alter Apophis's orbit through gravitational interaction with Earth. When an asteroid passes near a planet, tidal forces and gravitational acceleration change its trajectory, sometimes dramatically. The degree of change depends on how close the approach is and the relative velocities. Apophis will experience significant orbital deflection, changing its period around the Sunday and shifting its future Earth-crossing potential. Predictions for subsequent close approaches in 2036 and 2060. 8 involve larger uncertainties. Those future positions depend on the exact details of the 2029 encounter, details we can't measure precisely until the encounter happens. The distance closer than geostationary orbit makes this an unprecedented scientific opportunity. Telescopes will track Apophis continuously as it approaches, measuring its rotation state, mapping its surface features, determining its composition through spectroscopy, and measuring its size and shape with radar. The asteroid is roughly 370 meters in diameter, large enough to cause regional devastation if it ever impacted, but small enough that detecting surface details from Earth-based observations remains challenging. The close pass brings it within range of techniques normally reserved for near-Earth objects during even closer approaches. Radar astronomy will play a crucial role. Radio telescopes like the Goldstone antenna in California and the Arecibo replacement facility, assuming it's operational by then, can bounce radio waves off the asteroid's surface and analyze the echoes. Radar provides precise distance measurements, accurate to meters, rotation period measurements accurate to seconds, and surface roughness information that optical telescopes can't match. Delay Doppler radar imaging creates two-dimensional pictures. One axis represents distance, the time delay of the echo, and the other represents velocity, the Doppler shift of the echo. These radar images reveal shape, rotation, and surface features, sometimes detecting boulders, craters, and ridges only meters across. Rotation studies matter because asteroids spin, and their spin states carry information about their history. Apophis rotates with a period of approximately 30 hours determined from light curves measurements of how its brightness varies as different faces reflect sunlight toward Earth. This rotation rate is stable now, but the 2029 Earth encounter will change it. Tidal forces acting on the asteroid as it passes will tug its rotation, potentially speeding it up or slowing it down depending on the geometry. Measuring this rotation change provides data about the asteroid's internal structure, whether it's a solid monolith or a rubble pile of smaller pieces held together loosely by gravity. The Yarkovsky effect adds another layer of complexity. Asteroids absorb sunlight, warming their surfaces, then radiate that energy as infrared heat. This thermal radiation carries momentum, creating a tiny rocket effect that pushes the asteroid. For a rotating asteroid, the afternoon side is warmer than the morning side, and this asymmetric thermal emission creates a small but persistent force, either speeding the asteroid up or slowing it down in its orbit, depending on whether it rotates prograde with the solar system's spin or retrograde against it. Over millions of years, the Yarkovsky effect can change orbits significantly, shifting asteroids from the main belt into Earth-crossing trajectories. For Apophis, the Yarkovsky effect must be measured precisely to predict its long-term orbital evolution. The effect is tiny creating orbital changes of only meters per year, but those meters accumulate over decades into kilometers of position uncertainty. The 2029 close approach provides an opportunity to measure Yarkovsky acceleration by comparing the asteroid's actual position against predictions that don't include thermal effects. Any discrepancy indicates Yarkovsky influence, allowing calibration of models used to predict future encounters. Public perception represents a challenge and opportunity. Apophis has appeared in news headlines repeatedly since its discovery, usually accompanied by alarming language about killer asteroids and cosmic threats. The actual risk is low to negligible for any encounter calculated so far, but risk communication is difficult, explaining that there's a 1 in 45,000 chance of impact in 2060. 8. The current estimate means different things to different people. Statisticians understand it as negligible risk, far lower than countless risks we accept daily. But to someone unfamiliar with probability, 1 in 45,000 sounds concerning, like a real possibility. Rather than an essentially impossible event, proposals for Apophis missions have circulated in the planetary defense community, sending a spacecraft to rendezvous with the asteroid during or after its 2029 Earth encounter would provide close-up data impossible to obtain from Earth. Such a mission could characterize the asteroid's composition, internal structure, and surface properties in detail. It could also serve as a demonstration of deflection technology. Using techniques like kinetic impact, crashing a spacecraft into the asteroid, or gravity tractor, using a spacecraft's gravity to gently pull the asteroid to slightly alter Apophis's orbit, proving we possess the capability to protect Earth from future asteroid threats. NASA's DART mission, double asteroid redirection tests, successfully impacted the asteroid Dimorphos in 2022, demonstrating kinetic deflection. Works as predicted. The impact changed Dimorphos's orbit around its larger companion Didymos, proving humans can alter asteroid trajectories with sufficient warning time. An Apophis mission would build on DART's success, testing deflection techniques on a larger, potentially more scientifically interesting target. Conspiracy theories about NASA downplaying impact odds are predictable and unfounded, but psychologically understandable. Space agencies face a difficult balance between transparency and avoiding panic. Releasing every preliminary orbit calculation with its associated uncertainties creates alarm when uncertainties are large, even though large uncertainties are normal for newly discovered objects with limited observational data. Waiting until calculations are refined before making announcements risks accusations of cover-up. If someone discovers the object independently or leaks occur, NASA and other agencies have generally leaned toward transparency. Publishing orbit calculations and impact probabilities through the Sentry system and Torino scale a tool for assessing asteroid impact risks. But transparency doesn't prevent conspiracy theories. It just shifts them from covering up impacts to covering up deflection failures or alien involvement. The narrative frame of the asteroid that will brush Earth's cheek captures the mixture of danger and wonder these close approaches inspire. Apophis won't hit us, but it will come close enough that we'll feel its presence, watch it pass, see the cosmic machinery that occasionally delivers mountain-sized rocks to Earth's vicinity. The close pass reminds us that space is not empty, that debris from solar system formations still orbits out there, that occasionally that debris crosses paths with Earth, and that while we've been fortunate so far, luck doesn't last forever. Preparation matters, detection, tracking, characterization, and deflection capabilities represent humanity's insurance policy against the cosmic lottery that eventually delivers an impact. The event also serves as a global teachable moment. Planetary defense requires international cooperation. Asteroids don't respect borders, and a threat to one nation is a threat to all. The United Nations Committee on the Peaceful Uses of Outer Space COPUOS coordinates international efforts to track near-Earth objects and develop response capabilities. The 2029 Apophis flyby will likely trigger renewed interest in planetary defense funding and policy, potentially accelerating development of detection networks and deflection technologies. Looking ahead to the planetary parades of the 2040s provides context. The universe operates on schedules that ignore human timeframes. Asteroids arrive when orbital mechanics dictate. Planets align according to Kepler's laws. Comets fall from the Oort cloud following gravitational perturbations that started millennia ago. We mark these events on calendars anticipating them, preparing for them, but they unfold according to physics, not human convenience. Apophis will pass in 2029 regardless of whether we're watching, whether we care, whether we're ready. The indifference of the cosmos to human concerns is both terrifying and liberating. Part 12. When Planets Dance, September 20th, 2040. Mark it on whatever calendar system survives the intervening years, because on that date the solar system will present a geometric arrangement rare enough to attract attention, yet common enough that similar configurations recur with predictable frequency. 6 planets, Mercury, Venus, Mars, Jupiter, Saturn, and Uranus, will occupy a relatively narrow band of sky as seen from Earth. Their longitudes, angular positions along the ecliptic separated by less than 90 degrees. The media will undoubtedly call this a planetary alignment, or parade, though technically the planets won't line up in a straight line. They'll simply cluster in one region of the sky simultaneously visible from Earth's night side. The geometry works like this. Planets orbit the Sunday in approximately the same plane, the ecliptic, defined by Earth's orbital plane. From our perspective, planets appear to move along a path across the sky that follows the zodiac constellations. Sometimes planets spread around the entire ecliptic, visible at different times as Earth rotates. Other times, their orbital positions cluster, so multiple planets appear in the same region of sky simultaneously. These clustering events occur regularly, but irregularly, a result of planets with different orbital periods occasionally aligning their positions. Rarity depends on how many planets we require to participate and how tightly we define alignment. Getting all 8 planets within a 90-degree band happens every few decades. Getting them within 30 degrees happens every few centuries. Getting them in an actual straight line, all planets at 0 degrees separation, as seen from the Sunday, probably never happens within human timescales, because orbital periods don't share exact integer ratios that would create perfect recurring alignments. The 2040 event will be particularly favorable for observation. The planetary cluster will include bright naked eye planets, Mercury, Venus, Mars, Jupiter, Saturn, all easily visible without optical aid, plus Uranus, which requires binoculars or small telescopes. Neptune will be elsewhere in its orbit, not participating. The planets will be visible in the evening sky after sunset, rising together in the east and arcing across the southern sky, depending on observer latitude, providing hours of viewing opportunity. Amateur astronomers will have a field day. Capturing all visible planets in one wide-angle photograph becomes possible during these events, creating images that showcase the solar system's architecture. The different brightnesses and colors of the planets add visual interest. Venus shines brilliantly white, Mars glows distinctly orange-red, Jupiter is pale yellow-white. Saturn is similar to Jupiter but slightly fainter. Uranus barely shows as a pale blue-green disk, even in binoculars. Photographing them together creates a portrait of planetary diversity compressed into a single frame. Professional astronomers will seize opportunities beyond pretty pictures. Planetary alignments don't create special gravitational effects, despite persistent myths about triggering tides or earthquakes. But they do allow simultaneous measurements across multiple planets using the same instruments and techniques. Comparative planetology benefits greatly, measuring atmospheric properties of Venus, Jupiter, and Saturn during the same observation window controls for instrumental and observational variables, enabling more confident comparisons. The alignment may also aid in detecting unusual objects. When planets cluster, the background star field in that region gets observed more intensely than usual. Faint asteroids, distant comets, or even undiscovered planets in the outer solar system, like the hypothetical Planet 9, might be spotted by observers scanning the area for planets. Planet 9, proposed to explain orbital clustering of distant trans-Neptunian objects, remains undiscovered despite searches. Its predicted location, if it exists, wanders slowly through the zodiac, and it might happen to be near the 2040 planetary cluster region, making detection more likely simply because more telescopes will be pointed that way. Mythological and cultural contexts have surrounded planetary alignments throughout human history. Ancient astronomers tracked planetary positions carefully, noting conjunctions and alignments and attributing significance to them. Astrological traditions, which persist despite lacking scientific support, assign meaning to planetary configurations based on symbolism and perceived correlations. The scientific worldview rejects these associations as pattern, seeking applied to random coincidence. But the human psychological response to celestial alignments remains strong. When planets gather in one part of the sky, it feels significant, even if we intellectually understand it's just orbital geometry. Some fringe communities will inevitably predict catastrophic consequences from the 2040 alignment. Doomsday scenarios claiming planetary gravitational forces will cause earthquakes or weather disasters are recurring, yet unsupported by physics. The gravitational influence of other planets on Earth is negligible compared to the Moon and Sunday. Even when aligned, their combined pull adds only tiny perturbations to Earth's orbit, with no measurable effect on geological or atmospheric processes. But facts don't stop predictions. Someone online will claim the alignment will trigger disasters, others will believe and prepare, and when disasters fail to materialize, the predictions will be quietly forgotten or rationalized away. Hidden scientific opportunities in alignments include measuring the solar system's mass distribution. Precise tracking of planetary positions allows tests of gravitational theories and refinement of planetary masses. Every planet gravitationally affects every other, creating orbital perturbations that accumulate over time. By measuring where planets are and comparing to where Newtonian gravity predicts they should be, astronomers can detect anomalies hinting at unknown masses elsewhere in the solar system, or more speculatively deviations from gravitational theory itself. The cultural dimension of alignments as global events matters in an increasingly connected world. Unlike eclipses visible only from specific geographic locations, planetary configurations are visible globally, weather permitting. This creates shared experiences across cultures and continents. In 2040, people in Tokyo, New York, Sydney, and Lagos will see the same planetary arrangement. A moment of cosmic commonality that transcends political and cultural divisions. The metaphor of a planetary choir works well here. Each planet moves to its own tempo, Mercury racing around the Sun every 88 days, Neptune creeping along at 165 years per orbit. These different periods create complex rhythms and patterns over time. When planets cluster, it's like a moment in a long cosmic symphony where multiple instruments sound simultaneously, forming a chord before drifting apart again into individual melodies. The metaphor shouldn't be stretched too far. Planets don't actually make sounds or create music, but it captures something true about patterns and rhythms in orbital dynamics. Foreshadowing the 2015 supermoon creates narrative continuity. These alignment events and close approaches mark time on scales that transcend individual human lifespans. Simone, born in 2040, will be 12 when the next supermoon of note occurs, 20 when Apophis makes its next close pass, and middle-aged before the next major planetary alignment. These cosmic events serve as waypoints in generational memory, shared experiences that define eras and give structure to historical time beyond human constructs like decades and centuries. Part 13. The Moon That Touches Earth. November 9, 2022 will bring the closest lunar approach of the 21st century, a supermoon so extreme it stretches the definition of the term. The Moon's orbit around Earth is not circular but elliptical, meaning the Earth-Moon distance varies from about 363,000 kilometers at perigee, closest approach, to about 405,000 kilometers at apogee, farthest distance. This variation causes changes in the Moon's apparent size as seen from Earth. When the Moon reaches perigee during its full phase, appearing largest and brightest, we call it a supermoon. The November 2022 supermoon will occur at an exceptionally close perigee, bringing the Moon to approximately 356,500 kilometers from Earth's center. This is roughly 3% closer than typical supermoons and about 6% closer than average full moons. The distance difference may sound trivial in percentage terms, but apparent size depends on distance in non-linear ways. A 6% decrease in distance produces roughly a 13% increase in apparent diameter and a 30% increase in apparent brightness. At this closest approach, the size difference between this supermoon and an average full moon will be noticeable. Even without instruments, place a 2022 full moon photograph next to one taken at average lunar distance, and the contrast is obvious. The supermoon fills more of the sky, its features appear larger, and its brightness illuminates landscapes more dramatically. Under ideal atmospheric conditions, with the Moon near the horizon, the combination of actual size increase and the Moon illusion, a psychological effect that makes horizon-hugging moons seem larger than overhead ones, will create views that feel almost surreal. Photography opportunities will be extraordinary. Lunar photographers wait for supermoons to capture the Moon alongside landscape features, using its increased size to craft dramatic compositions. The 2022 event will offer this generation of photographers the ultimate chance. Planning will begin years in advance, scouting locations where the Moon will rise or set behind striking foreground subjects, calculating exact timing and positioning to get the perfect shot. The brightness boost has consequences beyond aesthetics. Moonlight in general is bright enough to cast shadows and influence nocturnal animal behavior. Supermoon light is brighter still, potentially casting sharp shadows from objects and illuminating landscapes to levels approaching twilight. Nocturnal animals that time their activities around lunar phases may respond to this unusual brightness. Predators that hunt using vision could gain an advantage over prey that rely on darkness for concealment, while prey species might alter their behavior, staying hidden during the brightest hours. Extreme tides represent the most significant physical consequence of close lunar approaches. Ocean tides arise from gravitational gradient, the difference between the Moon's gravitational pull on Earth's near side versus its far side. This gradient creates two tidal bulges, one facing the Moon, one opposite it. Earth's rotation carries coastlines through these bulges, producing the familiar twice-daily tidal cycle. Tide strength depends on lunar distance, Closer moons create stronger gradients and thus higher tides. Spring tides. The highest tides, occurring during new or full moons when the Sunday and Moon align, will be amplified during the 2022 supermoon. Coastal areas already experiencing high spring tides will see water levels several centimeters higher than usual. This may not sound dramatic, but during storm-driven high tides, those extra centimeters can mean the difference between water staying in channels and overtopping seawalls, flooding coastal infrastructure. Coastal flood warnings will likely be issued for vulnerable regions, especially those already grappling with sea level rise from climate change. Speculation about seismic coupling enters murkier territory. Some researchers have explored statistical links between lunar phases, tidal forces, and earthquake occurrence, searching for evidence that tidal stress on faults might trigger quakes already teetering on failure. The mainstream consensus is that any such effect, if it exists at all, is negligibly small. Faults fail when accumulated tectonic stress exceeds the friction holding them locked, and tidal stresses are orders of magnitude weaker than tectonic ones. However, faults already at the threshold of failure, even tiny additional stresses could theoretically act as a trigger. Studies have found weak correlations between tides and earthquakes in some fault systems, but not others, effects so faint they're hard to distinguish from statistical noise. The 2022 supermoon offers a natural experiment. If tidal triggering is real and measurable, we might expect slightly elevated global earthquake rates in the days around closest approach. If rates stay normal, it further supports the conclusion that tidal effects on seismicity are negligible. Cultural responses to the supermoon will likely blend celebration and anxiety. Festivals and public viewing events will draw crowds to dark sky locations, and famous landmarks, lunar eclipses, when they coincide with supermoons, become media spectacles attracting millions of viewers. Even without an eclipse, the record-setting nature of the 2022 event will generate widespread interest. Simultaneously, various doomsday predictions and apocalyptic interpretations will circulate online, claiming the close approach portends disaster. These predictions follow predictable patterns and will be equally predictably wrong, but they'll briefly capture attention and cause unnecessary anxiety for people unfamiliar with astronomical facts. The phrase, "the night that glowed like day," is an exaggeration, but it captures the qualitative experience of extremely bright moonlight. Human eyes adapt to darkness. Pupils dilate to collect more light, and photoreceptor cells boost sensitivity. In full dark adaptation, the range of human vision spans multiple orders of magnitude. Moonlight from a typical full moon lets you walk comfortably, read large print, and faintly distinguish colors. Supermoon light pushes this further, potentially allowing reading of normal print and more vivid color perception. Combined with high atmospheric clarity and dark surroundings, the experience approaches the illumination level of deep twilight. Atmospheric scattering studies benefit from bright moonlight, as lunar illumination provides a stable light source for measuring atmospheric properties. Research teams studying aerosols, clouds, and atmospheric chemistry sometimes use moonlight to calibrate instruments or extend observations beyond daylight hours. The supermoon delivers unusually high signal levels, potentially enabling more precise measurements or detection of subtle effects normally below detection thresholds. Citizen science projects could coordinate global observations of the supermoon, collecting data on apparent brightness, color, and atmospheric effects from observers worldwide. Similar projects have successfully gathered eclipse observations, meteor counts, and aurora reports, building datasets that supplement professional research while engaging the public in astronomy. The supermoon offers an accessible target. Anyone can observe and photograph it, lowering barriers to participation. Transitioning to discuss comets that may outshine even this supermoon sets up the final narrative beats. The moon at its closest approach is spectacular, but it's a regular phenomenon, a predictable highlight in a continuous cycle of supermoons that recur monthly to varying degrees. Comets, by contrast, are wildcards, unpredictable visitors that occasionally rival or exceed the moon in brightness, but do so rarely and without reliable schedules. This comparison highlights two distinct types of cosmic phenomena: the predictable, cyclic motions of bodies locked in regular orbits versus the chaotic, punctuated appearances of comets falling from the outer darkness. Part 14, 2060, the brightest comet ever. In 2060, something will happen that no living human has ever witnessed. The forecasts are already in, the orbital calculations done. and astronomers are marking their calendars for an event that will rival anything in recorded history. A massive object from the Oort cloud, the distant reservoir of comets surrounding our solar system, is heading toward the inner solar system on a trajectory that will bring it close enough to the Sunday to become spectacular. Not just bright, not just visible, but potentially as luminous as the moon itself, dominating the night sky for weeks or even months. If the predictions hold, this comet will be the astronomical event of the century, a once-in-a-lifetime spectacle visible even in daylight, casting shadows at night, and fundamentally changing humanity's relationship with the sky for everyone alive to see it. Let me put this in perspective. Most comets passing through the inner solar system are faint, requiring binoculars or telescopes to detect. A handful per decade become visible to the naked eye, appearing as fuzzy patches of light with modest tails. Every few decades we get a bright comet, something that makes headlines and draws people outside to look up. Comet Hale-Bopp in 1997 was one such object, visible for over 18 months and bright enough to see easily from cities despite light pollution. Before that, Comet West in 1976 put on a spectacular show for those who woke before dawn to witness it. And of course, there's Halley's Comet, which returns every 75 to 76 years and has been documented by humans for over 2,000 years in Babylonian records, Chinese chronicles, and even the Bayeux Tapestry. But even Halley's Comet at its best is just a bright comet, impressive, but not sky-dominating. The 2060 comet, if it lives up to its billing, will be exactly that. Sky-dominating current models suggest it could reach an apparent magnitude of -10 or even -12, making it as bright as a half-moon or possibly a full moon. To understand what this means, you need to know the magnitude scale is logarithmic and inverted. Smaller numbers mean greater brightness. The Sunday has an apparent magnitude of -26.7. The full moon -2.7, Venus at its brightest about -4.9, and a bright comet like Hale-Bopp topped out at around -1. Each magnitude step represents roughly 2.5 times more light. So a -12 magnitude comet isn't just 11 times brighter than Hale-Bopp, it's thousands of times brighter. What creates such a spectacular comet? Size matters. Obviously, the nucleus of the 2060 comet is estimated to be enormous, 50 to 100 kilometers across, making it one of the largest objects ever to visit the inner solar system from the Oort cloud. For comparison, Comet Hale-Bopp's nucleus was roughly 60 kilometers wide, already considered huge. But size alone isn't enough. A comet also needs to pass close to the Sunday, close enough that solar heating vaporizes massive amounts of ice, creating a coma, a gaseous envelope, that can grow larger than Jupiter and a tail that stretches hundreds of millions of kilometers. The 2060 comet checks all these boxes. Its perihelion will bring it within about 0.3 astronomical units, roughly 45 million kilometers, inside Mercury's orbit. At that distance, solar heat will vaporize not just water ice, but also more volatile compounds like carbon monoxide and carbon dioxide. But beyond the science, something deeper is at play. For one brief moment in 2060, humanity will share a common experience. People in every country, on every continent, will look up and see the same thing. A comet so bright it cannot be ignored, so spectacular it transcends language, culture, and politics. The 2060 comet will be impossible to miss. It will dominate the twilight and nighttime sky, visible even from brightly lit cities, and cast enough light to read by in dark locations. And here's where things get interesting, maybe a little unsettling. What happens when you introduce a light source into the night sky that rivals the moon? We know moonlight affects ecosystems. Nocturnal animals adjust their behavior with lunar phases. Predators hunt differently during full moons. Human circadian rhythms, the internal clocks regulating sleep-wake cycles, are influenced by ambient light. For as long as humans have existed, the moon has been the brightest object in the night sky. What happens when we add a third variable to that equation? The truth is, we don't know. The comet will be visible for weeks, possibly months, pumping light into the nighttime environment, at levels Earth hasn't experienced from a comet in recorded history. Now, let's address the less pleasant possibilities. Whenever a comet comes this close to Earth, people worry about impacts and catastrophes. Let me be clear, the 2060 comet will not hit Earth. Its orbit is well characterized and it will miss us by millions of kilometers. but that doesn't mean it's completely harmless. Comets shed material as they approach the Sunday dust, small particles, even larger fragments, that spread along their orbits. If Earth's orbit intersects the comet's trajectory after it passes, we could encounter this debris stream, creating a spectacular meteor shower. A more concerning scenario, though extremely unlikely, is not impossible. Comets sometimes break apart as they approach the Sunday. Thermal stress. Tidal forces and outgassing pressure can cause structural failure in a comet's nucleus. If the 2060 comet fragments, and if one of those fragments ends up on a trajectory closer to Earth than predicted, we'd face a problem. The odds are vanishingly low, but not zero, which is why asteroid and comet tracking has become such a critical endeavor. Fortunately, humanity is prepared. NASA will launch the NEO Surveyor, an infrared space telescope, in the first half of 2026. This instrument will enable day and night observations of near Earth objects. NEOs, including those passing between Earth and the Sunday, something ground-based optical telescopes cannot do. But hopefully, all will be the dominant response. Because whatever else it is, the 2060 comet will be beautiful, a reminder that we live in a universe capable of breathtaking phenomena. For weeks or months, dinner conversations will turn to tail structures and coma dynamics. Children will stay up late to see the comet. It will become part of that generation's cultural fabric. And when it's over, when the comet has swung around the Sunday and is heading back to the outer solar system, we'll be left with photographs and memories. But even as it fades, another date on the cosmic calendar looms, a milestone equally profound. Part 15, 2177. Pluto's first birthday and cosmic reflection, on February 18, 1930. A young astronomer named Clyde Tombaugh was examining photographic plates at the Lowell Observatory in Flagstaff, Arizona. He was searching for a predicted ninth planet, a world beyond Neptune that might explain slight irregularities in the outer planet's orbits. The work was tedious, comparing pairs of photographs taken days apart, looking for anything that moved against the background of stars. And then he found it a tiny dot that had shifted position between exposures. Planet X, the ninth planet, Pluto. The discovery made headlines around the world. Pluto was the first planet discovered by an American, and it captured public imagination in ways few astronomical discoveries do. The name Pluto, suggested by an 11-year-old English girl named Venetia Burney, seemed perfect, the god of the underworld for the distant, dark world at the solar system's edge. For 76 years, schoolchildren learned the solar system had 9 planets, and Pluto, tiny and mysterious, was the last outpost before the great darkness of interstellar space. Then, in 2006, the International Astronomical Union, IAO, redefined what it means to be a planet. Pluto met 2 of the 3 criteria, but failed the 3rd. It had not cleared its orbital neighborhood of other debris. Under the new definition, Pluto was reclassified as a dwarf planet, and the solar system returned to 8 planets. The demotion sparked surprising public outcry. People felt affection for Pluto, this distant underdog world. But here's a fact that puts all this in perspective. In 247 years after its discovery, Pluto will complete exactly 1 orbit around the Sunday. It will return to the same position in space where Clyde Tombaugh first spotted it on those photographic plates. Think about what that means. Pluto's year, the time to finish 1 orbit, is 247.9 Earth years. When Pluto was discovered in 1930, it had completed only about 36% of 1 orbit since the US Declaration of Independence was signed 1776. We found it, studied it, sent a spacecraft to fly by it in 2015, watched it get demoted and debated, and through all this, Pluto hasn't even finished 1 lap around the Sunday. This is a profound lesson in timescales. Humans live, at best, 80 to 100 years. That's the span of direct memory and experience. For any individual, all civilizations last longer, with continuous written records stretching back about 5,000 years. But even on that scale, Pluto has completed only about 20 orbits. The entire span of human civilization covers just 20 years for this distant world. Zoom out further to the solar system's 4.5 billion-year history, and Pluto has completed roughly 18 million orbits. That sounds like a lot until you realize Earth has completed 4.5 billion orbits in the same time. But Pluto is not alone. The outer solar system operates on timescales that dwarf human experience. Neptune takes 165 years to orbit the Sunday. Since its discovery in 1846, it has barely finished more than one orbit. Uranus takes 84 years, Saturn takes 29. These are worlds that move through the zodiac at a stately, almost imperceptible pace. Ancient astrologers knew only 5 planets beyond Earth, because those are the only ones that shift noticeably across the sky within a human lifetime. This raises an interesting question. What's the longest timescale humans can truly comprehend? We can intellectually grasp that the universe is 13.8 billion years old, that the Sunday formed 4.5 billion years ago. We can recite these numbers, put them in textbooks, teach them to students, but do we feel them? Can any human mind truly hold 13 billion years of time in a way that feels real? Probably not. Our intuition is calibrated to human lifetimes, to the years we expect to live. Beyond a few generations, time becomes abstract. That's why Pluto's first birthday since discovery is such a poignant marker. It's a timescale just barely comprehensible to our civilization. 247 years spans from 1777 to 2177, over a century and a half into our future. It's longer than any human life, longer than most institutions survive, but short enough to trace cultural continuity. People in 2177 will be able to look back at records from Pluto's discovery and understand what those astronomers were doing and why it mattered. But when Pluto completes that first orbit in 2177, it will only be beginning its second orbit since discovery, and that second orbit will take another 247 years. Pluto won't finish a third orbit until 2671. The people who witnessed Pluto's second birthday haven't been born yet, won't be born for centuries. And by then, will humans still care about Pluto? Will we still watch the skies, track the planets, mark these cosmic milestones? I'd like to think we will. Despite everything, despite the chaos that often defines human behavior, we've maintained astronomical observatories for centuries. We've kept records, passed down knowledge, built on the discoveries of previous generations. The fact that we can calculate Pluto's orbit and predict its position in 2177 is a testament to the power of accumulated knowledge, humans working across generations toward shared goals. Speaking of long-time scales, consider this. When 3IATLAS entered our solar system in 2024, it had been journeying through interstellar space for millions of years. If it was ejected from a star system 10 light-years away, traveling at 66 km/h, it would have taken about 45,000 years to cover that distance. For all that time, this comet was frozen, unchanged, drifting through the void. Then it spent a few months in our solar system, was destroyed by the Sunday, and was gone. But understanding is not the same as experiencing. We can calculate Pluto's orbit, but we can't feel what it's like to take 247 years to circle the Sunday. We can measure the Sunday's lifetime at 10 billion years, but we can't viscerally grasp that span of time. We are bounded by our biology, our mortality, our place in space and time. When Clyde Tombaugh discovered Pluto in 1930, he was 24 years old. He died in 1997 at age 90 having lived to see spacecraft visit every planet in the solar system, to see humans walk on the moon, but he never saw Pluto complete an orbit. No human alive when Pluto was discovered will live to see its first birthday. That milestone will belong to people not yet born.